In March 2024, Russia was launching 3,500 glide bombs per month against Ukrainian targets with devastating precision, a 16-fold increase in 2023 numbers. And while the data for the first half of 2025 is mixed, the numbers are bound to only get higher. These satellite-guided weapons can strike from up to 60 miles away, from distances that can keep Russian aircraft safely beyond the reach of most air defense systems. The system was practically revolutionary, as it bypassed the need for conventional air force support, which Russia didn't have much of in the first place. But by February 2025, the tide had completely turned. Russian military bloggers reported that all satellite correction systems have officially left the chat, with Russian forces now requiring up to 16 bombs to achieve the same destructive effect that previously required just one. The change wasn't luck, but Ukraine being innovative in the face of adversity. Innovations such as Lima. Lima is an electronic warfare system so sophisticated that it doesn't just jam Russian navigation signals, it confuses them. Moscow's pilots think their precision weapons are flying toward legitimate targets, but in actuality, Ukraine's automated systems are feeding false data into Russian guidance systems. The bombs instead are being directed into empty fields many kilometers from their intended impact points. This isn't just a major tactical success, it's already revolutionized the war going on in the skies above Ukraine. The system doesn't just force bombs off course, it can blind Russia's entire air force. Let's dive into how Lima came to be, how it works, and its potential going forward. To understand Lima's revolutionary impact, we need to delve into what was considered the biggest threat to Ukraine in 2023 and 2024: glide bombs. Russia's use of glide bombs lies in pure convenience, stemming from multiple factors. First, Russian air forces failed to exert air supremacy over Ukraine in the vital first few months. This was due to a complex combination of military doctrine, logistics, and lack of adaptation, which we'll discuss a bit later. But the gist was that Russia couldn't use its arguably modern jets due to Ukraine's layered defenses. Ukraine had received vital supplies of anti-air defenses that could threaten Russian aircraft, requiring Russia to withdraw its jets from flying missions in or around Ukraine's airspace. Secondly, Russia was encountering a bottleneck in production. The supposed modern missile designs, Shahid drones, and conventional artillery that Russia had at its disposal couldn't be manufactured in large enough numbers to make up for the increasing losses during this attritional warfare that the sides had settled into by the end of 2022. This is largely due to the sanctions imposed by NATO countries that prevented Russia from accessing advanced technology, including microchips that were required for advanced avionics and navigation. Finally, Russia was already advancing its electronic warfare capabilities, specifically with the use of drones, to match Ukraine on the front lines. This meant that Russia could leverage similar surveillance capabilities to find vital stationary military targets at both shorter and longer ranges. The glide bombs solved all these issues through the UMPK, Russian for Unified Gliding and Correction Module. A UMPK is not a revolutionary design in itself, but a simple add-on for existing unguided gravity bombs that would otherwise be dropped from bomber aircraft. The UMPK adds wings and a tail section to improve aerodynamics, as well as a rudimentary guidance system to allow the bomb to actively swerve and change course mid-flight. The US has an equivalent system with its JDAM, the Joint Direct Attack Munition, a guidance system that can be attached to bombs from the Cold War, making them still devastating in modern times. For Russia, UMPKs allowed it to use its extensive stockpiles of Soviet-era ordnance, particularly the Fab High Explosive Aviation Bombs, or Fugasnaya Aviatsonaya Bomba models. The Fab 500, which holds 470 pounds of explosive, was among the first bombs retrofitted with UMPKs and developed into glide bombs that were used in Ukraine. After that came its cousins like the Fab 250, Fab 1000, and even the ludicrous Fab 3000, which carries around 3,000 pounds of explosive material. Best of all, these bombs allowed Russia to manufacture glide bombs at scale. There's plenty of base material in the Soviet stockpiles, and each UMPK costs around $24,000, and the navigation relies on guidance systems that already existed and were deployed throughout Russian military equipment. These costs are negligible compared to standard precision-guided long-range missiles and interceptors, both of which have price points in the millions of dollars. This resulted in Russia deploying 40,000 bombs in 2024 alone. And according to the Royal United Services Institute, the RUSI, Russia plans to produce 75,000 glide bombs in 2025, allowing it to launch an average of 205 per day. The use of glide bombs allows Russian aircraft, both from the Soviet era and more modern designs, to deploy glide bombs from around 30 to 50 miles away from the front line, thus keeping them on the Russian side of the airspace and much safer from a potential counterattack. Considering that Russia still maintains a sizable lead in the number of fighter aircraft it has at its disposal, it can also conduct attacks from multiple vectors, overwhelming defenses that rely on high-effect and high-cost singular systems like interceptors or air-to-air missiles. Even more concerning for Ukrainian defenders, Russian forces claim that UMPK-equipped Fab 3000s achieve a circular error probable (CEP) of around 33 feet. This meant that half of the bombs would fall within 33 feet of the intended target. Additionally, the Institute for the Study of War suggested that Russia had improved UMPK designs in early 2025, dropping the CEP from 160 feet to under 16 feet across the available arsenal. Of course, this CEP relies on the system maintaining constant communication with satellites, which is what Lima specifically interrupts. But before we go into the specifics of how the system that shoots down glide bombs functions, it's vital to note why exactly this development came from Ukraine itself. After all, you'd think that countries like the US, UK, France, or Germany would be the first to design anti-glide bomb systems. After all, they might have more than capable electronic warfare capabilities natively, but the issue lies with their ability to implement them in Ukraine. When Russian glide bombs started raining down, Ukraine's initial defensive response followed conventional military thinking that worked for much of 2022, requesting advanced defense systems from Western allies. However, this wasn't going to be a viable approach in the long term for a few reasons. The first setback that Ukraine faced was long procurement and delivery times for conventional military equipment. Advanced Western air defense systems required months of bureaucratic approval processes, with each NATO member nation holding potential veto power over sensitive technology transfers. Even when systems were approved, training Ukrainian operators on complex Western equipment required additional months, while Russian glide bombs fell daily. Then came the simple economics of ammunition exchange, with over 3,000 glide bombs being used monthly since the start of 2024, and that number expected to rise into the 6,000s by the end of 2025. Expensive interceptor missiles that were donated by NATO simply were unsuitable for the task. Ukrainian forces couldn't afford to fire million-dollar interceptors at $24,000 guidance kits tacked onto bombs that Russia could dredge up from one of its many depots across Siberia. Additionally, Western electronic warfare is designed with mobility and integration over a large area in mind. The US and Europe have their own independent geolocation satellite systems, multiple military bases across the world, and the ability to deploy their air force deep into enemy airspaces. This allows them to exert significant pressure across the field, exert air superiority from day one, and potentially isolate an enemy in a theoretical war. In contrast, Ukraine needs area denial capabilities to prevent it from being invaded by a much larger enemy, with the system operating continuously in a contested airspace where both sides' air force are effectively dissuaded from flying. And even if advanced systems could be implemented, NATO was responsible for providing vital intelligence and operational support, which was a problem because the US had basically switched stances on providing donations to Ukraine under President Donald Trump. In March 2025, the US briefly suspended intelligence cooperation with Ukraine due to operational security concerns, with the hope that the suspension would pressure Ukraine and Russia to approach the negotiating table. Since then, those efforts failed. The US reduced its total commitment to Ukraine, resumed intelligence sharing, and completely abandoned efforts to broker a peace deal. While temporary, the interruption in intelligence sharing demonstrated how quickly external support could be disrupted by political considerations beyond Ukraine's control, and there's no telling if something similar can happen later, especially given that Starlink is one of the key intelligence providers to Ukraine's systems. Starlink is owned by Elon Musk, who already has problematic ties to the US and whose stance could change if the US political support does. So Ukraine was practically forced to develop a system from scratch using domestic production and technology. Ukrainian engineers began developing the Lima electronic warfare system as early as December 2022, when Russian glide bomb attacks were reaching peak intensity at the time. The timing reflected Ukraine's most desperate operational requirement, finding a way to counter precision weapons that were systematically destroying defensive positions. Luckily, the development program could leverage Ukraine's unique advantages in electronic warfare against Russia. Namely, older and more experienced Ukrainian engineers also possessed intimate knowledge of Russian navigation systems, since they worked with GLONASS, the global navigation satellite system that was developed back when Ukraine was in the Soviet Union. Research institutions in Kyiv and Kharkiv were at the forefront of Soviet-era computing during the Cold War, laying a foundation of technical expertise that continues to inform Ukraine's modern electronic warfare capabilities. The Lima system was also developed by the so-called Night Watch team, originally a group of civilian volunteers with backgrounds in business and manufacturing, who later brought in specialists with expertise in Russian missile guidance systems to help craft advanced electronic warfare and drone countermeasure solutions. Unlike Western development programs that might require years to move from concept to deployment, Ukrainian engineers operated under the urgent pressure of daily bombardment. While this all might have led to hastened approaches that could mean errors, it also completely bypassed traditional bureaucratic and administrative delays and shortened the time from prototype to testing to mass production to months rather than years. Early prototypes focused on traditional jamming approaches, overwhelming Russian navigation signals with electronic noise. However, testing revealed that simple jamming could be countered by signal processing improvements or frequency hopping techniques, including adding more antennas, as in the aforementioned report of improving accuracy. The breakthrough came when engineers realized they could do something far more sophisticated. Instead of blocking Russian navigation signals, they could corrupt them with false data. According to Forbes reports, Nightwatch could produce up to 300 Lima units per month if required, indicating substantial domestic production capacity. In the end, the Lima system operates through digital suppression methods, combining jamming, spoofing, and cyber interference targeting navigation receivers, fundamentally different from traditional electronic warfare approaches. To understand exactly what that means, we need to go back to the systems that allow Russian glide bombs to be effective in the first place. GLONASS is the main competitor to the American-designed GPS. GLONASS consists of 24 satellites and 2 spares equally distributed in orbital planes inclined at 64.8 degrees from the equator, flying in roughly circular orbits at an altitude of 19,100 kilometers, which is slightly lower than the 20,200 kilometers altitude of GPS. However, GLONASS is more precise at higher latitudes, meaning nearer the poles, since GPS satellites orbit closer to the equatorial plane. More importantly, out of the 24 satellites, 18 cover the territory of Russia at any given time. Beyond geographical constraints, GLONASS satellites transmit the same code at different frequencies using FDMA, Frequency Division Multiple Access, while GPS uses different codes at the same frequencies through CDMA, Code Division Multiple Access. A receiver, i.e. the device that needs its position calculated, contacts 4 different satellites. 3 of the satellite signals are used to trilaterate the location of the receiver on Earth or in the air, while the 4th collaborates the time delay between the devices to ensure a horizontal accuracy of under 30 feet globally. More importantly, Russia has a specific coding system that provides high-level codes for military use. In the right circumstances, this should improve accuracy for both stationary and mobile targeting. The Russian UMPK-equipped bombs rely on dual navigation systems, inertial guidance, and satellite-based correction through GLONASS. When the satellite connection is lost, bombs continue their flight using only inertial data. This allows the system to theoretically calculate its position relative to the target based on flight time and velocity, but compounding approximations cause it to lose precision the longer it flies. Lima exploits both of these guidance methods simultaneously. For satellite navigation, Lima generates counterfeit GLONASS signals with higher levels than authentic satellite transmission, ensuring Russian receivers lock onto the falsified data instead of legitimate navigation information. For inertial navigation systems, Lima introduces fake flight data into the bomb's onboard computer, corrupting the initial position data that inertial systems use as reference points. Essentially, the bomb might interpret data that suggests it's flying from a different spot, causing it to swerve out of the way to compensate. And without the satellite correction, once it does, there's no way to turn it back. Of course, the actual accuracy and success rate of the system will likely remain a military secret until the war is over, or even long after it. However, we can glean some insights from the US competitor system, JDAM. Comparative analysis showcased in the Militani outlet, citing JDAM's own project office, shows that JDAM systems achieve a CEP of 3 to 16 feet when using GPS guidance. Without satellite navigation, JDAM accuracy degrades significantly, reaching an error of about 98 feet after 100 seconds of flight, based on inertial guidance alone. Russian UMPK systems are expected to experience similar degradation patterns, but with worse baseline performance, owing to JDAM's greater accuracy at peak efficiency. The analysis suggests that the CEP could rise to 150 or even 300 feet after 100 seconds of flight. Additionally, under Lima's electronic obfuscation, accuracy degrades exponentially. This means that the longer the incoming bombs remain in Lima's transmission range, the more errors accumulate in navigation calculations. If the bombs are dropped at subsonic speeds, slower than the speed of sound, they likely have to travel longer than 100 seconds. A simple calculation of a flying object that glides at the speed of sound shows that it'd need around 204 seconds to cover a distance of 45 miles. The physics behind glide bombs might require an entirely different video, but in a nutshell, air resistance plays a large role in limiting the speed of passive flight, meaning one without propulsion. The effectiveness of Lima became apparent as Russian bombing accuracy plummeted, particularly around regional centers like Kharkiv and Zaporizhia. Russian forces abandoned tactics of targeting these areas. Israeli military observer Yigal Levin assessed that innovations have made Ukrainian electronic warfare technologies the most advanced. with the Lima jammer representing one of the recent successes in disorienting Russian guidance systems. Most telling are inadvertent confirmations from Russian sources. The pro-Russian fighter-bomber Telegram channel, run by a former Russian military pilot, acknowledged that the golden era of the divine UMPK turned out to be short-lived, and that Ukrainian electronic warfare had become so effective that they saturate the front line, meaning that all high-value targets for Russian glide bombs are now covered by defensive systems. Russia has attempted various countermeasures with limited success. Russian forces use domestically produced anti-jamming Cometa-M antennas in UMPK kits, initially equipped with 4-element antennas, later upgraded to 6, 8, and eventually 16 and even 24 receivers. However, simply increasing the number of elements doesn't seem to have maintained UMPK's effectiveness at satisfactory levels. Perhaps the most damning evidence of Lima's effectiveness comes from how Russia has been forced to try and adapt to its failures rather than push for its numerical advantage. Multiple reports were already describing Russian aircraft equipped with commercial GPS units secured to instrument panels with improvised mounting systems. It's a clear signal that military GLONASS systems have become unreliable in Ukrainian airspace. What's worse, the reports come from as early as 2022, showcasing that Russia was already having to recalibrate its failing systems before Lima was finalized. With GLONASS being ineffective at its base, the glide bombs are likely even worse off when actively jammed than analysis would suggest. Lima also represents a decisive cost exchange victory for Ukraine. Each Lima system potentially neutralizes thousands of expensive Russian weapons, while costing a fraction of traditional kinetic air defense solutions. Unlike traditional systems like Russia's S-300 and American Patriot missiles, electronic warfare makes weapons miss rather than requiring expensive interceptors to destroy them. Furthermore, once developed and deployed, the system is essentially permanently active until it's turned off. There's no need to restock it with more missiles worth hundreds of thousands of dollars or more, depending on the system, or to constantly move the system so it doesn't get targeted. Since it jams the GLONASS system Russia uses across its military, it also has a measure of passive shielding against precision weapons that would be utilized to pressure it. Finally, there's the manufacturing capacity of the system. As mentioned, Ukraine could feasibly make 300 of the systems per month, compared to the 10 Patriot systems that Ukraine allegedly has, and possibly another 17 on their way in the spring of 2026. This is still only 27 systems meant to cover at least 800 miles of active front line, as well as any additional vectors that Russia decides to operate from and Ukraine's possible incursions into Russian territory. Simply put, the Lima system's relatively small economic and manufacturing load means that Ukraine could feasibly cover more of the front line with it rather than traditional interception-based systems. Furthermore, if the system's specifications are shared with NATO, Western countries can use their own production to improve those numbers. This wouldn't be out of the realm of possibility, given that Ukraine and NATO have already established the Joint Analysis, Training and Education Center in Poland to further one another's defensive systems. The success of Lima against Russian navigation systems opens several promising avenues for expanded electronic warfare capabilities. The same signal deception principles could be applied to longer-range precision weapons, including cruise missiles and ballistic missiles. Corrupting navigation data during terminal flight phases could significantly reduce accuracy against high-value strategic targets. As warfare increasingly relies on unmanned systems, electronic warfare capabilities that can corrupt drone navigation and communication links become critically important. Lima's approach is likely already being adapted to redirect entire drone swarms away from their intended targets. Even modern artillery increasingly relies on GPS guidance for precision fires. Electronic warfare systems that corrupt artillery navigation could create large defensive zones against precision rocket and artillery systems. When combined with traditional systems, deception can become redirection. A similar system to Lima, and employed on a larger scale, could potentially redirect a larger missile into an area covered by traditional interception systems, improving the latter's accuracy, use cases, and effective coverage. For military planners worldwide, Lima's success provides crucial lessons that will be studied for generations. In an era where weapons systems depend heavily on satellite navigation, the ability to corrupt or manipulate these systems may prove more valuable than traditional kinetic capabilities. Ukraine's achievement shows that technological superiority isn't determined by who has the most satellites or the biggest bombs, but by who can adapt and make the enemy's technology work for them instead. Thanks for watching, and if you'd like to learn more about the glide bomb strategy over Ukraine, watch this video. And if you'd like to stay up to date with the most recent developments in global geopolitics and war, subscribe to The Military Show.